So today we are going to talk about that last property of negative feedback amplifiers, the modification of input and output impedances. And we're going to do that as part of a different discussion. So we are going to introduce the four different types of negative feedback amplifiers: our voltage amplifier, transconductance amplifier, transresistance amplifier, and current amplifiers today. And then for the remainder of the quarter, we're going to work our way through example problems from each of those types of amplifiers. So let's start here. Types of amplifiers. And we're going to talk about how we classify. Okay? So our basic principles are how we sense signals at the output, and then how we mix or return signals at the input. Okay. So for sensing, we have two different options. All right. So let's consider this guy. I'm going to try to draw something here. Unfortunately, there's going to be a reasonable amount of drawing today. So let's say that this represents the output stage of our open loop amplifier circuit. And here are our output terminals. So this is where we measure our output voltage quantity, V out, and then down here below it, we are going to have the input portion of our feedback network. Now I'm going to call this port 2. We'll talk about that in a little bit, okay? So our first option is that we connect our output in parallel. Bless you. We connect our feedback network in parallel to the output of our open loop amplifier whenever we are trying to measure or sense a voltage signal. Okay, so this is our voltage sensing configuration. And in this voltage sensing configuration, our output resistance with feedback, ROF, will be equal to RO divided by the amount of feedback, where RO is the characteristic output resistance of the open loop amplifier. Okay, so hopefully you all remember from circuits 2, but if not, I understand because it's been quite a while for you guys. We can characterize any amplifier by its open loop voltage gain, which we're describing as A, its input resistance, which we're going to describe as Ri, and our output resistance, which we're going to describe as R0. So in a voltage sensing configuration, where our feedback network is connected in parallel to the output of our open loop amplifier, what happens is that the feedback tends to decrease the output resistance of the system, such that our output with feedback, or excuse me, our output resistance with feedback is simply the output resistance of the open loop configuration divided by the amount of feedback. We'll get into the math of why that happens in that particular way in just a little bit. Okay. Our other option for sensing is to connect our network in series. So let me try to draw this again real quick. Here's our open loop amplifier. Here is our output of our open loop amplifier. Then we're going to have our feedback network. This is again port 2. And so in a current sensing configuration, we connect our feedback network in series. So what I'm going to do here is I'm just going to break this loop real quick, and I'm going to wire this guy up. So our feedback network is in series. I'm going to short circuit my output terminals, and we are going to define our output current, I out. It's flowing in this direction. And if we look in to our shorted out output terminals, we're going to see our output resistance with feedback is R0 times 1 plus Ka. Okay. So in a current sensing configuration where our feedback network is connected in series, we boost the output impedance of our open loop amplifier configuration. Okay. So these are our two options for how we sense signals, right? Anytime we want to sense a voltage signal, we connect the feedback network in parallel. Anytime we want to sense a current signal, we connect the feedback network in series to the output stage of our open loop amplifier. And in doing so, our parallel configuration tends to decrease our output resistance of the system, and our series configuration tends to increase the output resistance of our configuration. And the amount of decrease, or the amount of change, I guess, in the output resistance is related to the amount of feedback that is applied. Okay. So we either boost it in a series connection or attenuate it in a parallel connection. So now let's talk about mixing. So we're going to be looking at the other side. Okay. So this is mixing or returning. All right. So now we're going to be looking at the input side of our open loop amplifier and the output side of our feedback network. So for voltage mixing, we are going to connect our feedback network in series. Oops, that's too high. like so. Here is our input voltage signal, right? This quantity right here, VI, is the input signal across the terminals of our open loop amplifier. And then this voltage right here is our feedback voltage, where this is port 1 of our feedback network. The current that's flowing in to our open loop amplifier, I'm going to call I sub I. So this is our input current into our open loop amplifier. V sub I represents the input voltage to our open loop amplifier. And then VF is our feedback voltage. And then we can see that we get voltage mixing effectively by just applying Kirchhoff's voltage law around this input loop, right? So we can see pretty easily here that Vs is equal to Vi plus Vf, or another way to put this would be Vi is equal to Vs minus Vf, which is exactly what we saw in our signal flow diagram representation. Okay, so we're doing the exact same thing that we've been doing for the last several classes, but we're finally bringing it back around to actual circuits, or that's what the goal is for today, all right? So whenever we have voltage mixing, we are going to tend to boost the input resistance. So our input resistance with feedback will be Ri times 1 plus Ka. So we scale it up. Exactly what we saw when we looked at a non-inverting amplifier way back in circuits 2, negative feedback. And yeah, so this is what our voltage mixing looks like. So anytime we have a voltage input signal, this is what we need to do. Anytime we are dealing with a current input signal, then we're going to wind up connecting our feedback network in parallel. So let me try to draw this really quickly. Current mixing, sorry. And we're going to have things in parallel here. So we should see something like this. Here's port 1. Here is our signal source, IS in this case. This is our current II being fed into the input of the open loop amplifier. This is our current IF. And then here is our voltage VI for the input terminals of our amplifier. And in such a configuration, we find that our input resistance with feedback is made smaller, so that we'll have Ri over 1 plus Ka. So from this, we have 4 different possible feedback topologies, okay? I'm just going to draw a simple table here. Amplifier type, input, output, and then return mechanism and the sense mechanism. Okay. All right, so for a voltage amplifier, meaning that our input signal is a voltage and an output signal is a voltage, we have what's called a series shunt connection, where shunt effectively just means you place something in parallel, right? So that means our input signal, or the feedback network, is applied in series with the input side of our open loop amplifier, and the feedback network is connected in parallel to the output side of our open loop amplifier. Then we have a transconductance amplifier, where the input signal is a voltage, the output signal is a current, and we call this a series feedback topology.
I didn't get that.
Shut up, watch. We have current amplifiers, where the input signal is a current, the output signal is a current, and so this is a shunt series configuration. And then finally, we have trans resistance amplifiers, where the input is a current, the output is a voltage, and so this is a shunt configuration. So from this, we can actually infer just a couple of things here pretty easily. For a good voltage amplifier, the expectation is we're going to have a very large input impedance and a very small output impedance with feedback. For a transconductance amplifier, we're going to have a very large input impedance and a very large output impedance. We use these as buffers a lot. For current amplifiers, we have shunt, so this is a low input, high output impedance. And then for a trans resistance, we have low input impedance and low output impedance, right? So we can figure out how we need to connect things to our open loop system in order to get our desired properties. All right, so next we are going to look specifically at feedback voltage amplifiers, or the series shunt configuration, right? So we're going to start by looking at an ideal or idealized case. And in our idealized case, we are going to assume, I'm going to write this down here, assume that our source Vs has no internal resistance, meaning that R sig is equal to 0. There is no load connected, which means that RL is equal to infinity. And that our feedback network, which I'm going to call our K network, does not load the amplifier. So we're going to break this down effectively into two circuits that are connected together. Okay. My topmost circuit, I'm going to call my open loop gain circuit, or my A circuit. And because we have a voltage amplifier configuration here, we're just going to use the practical voltage amplifier model like we developed back in circuits 2. Okay. So by that, I mean specifically, I'm going to have something that looks like this. My voltage amplifier is characterized by some input resistance, Ri. I'm going to have some input voltage, Vi. And so that's the input side of my open loop circuit. The output side of my open loop circuit is going to have my open loop gain multiplied by my input signal, and typically characterized by some output resistance R0. All right. I'm going to put a box around this. And sorry, just in case I need to reference it, which I know I will for this derivation, I'm also going to include my input current, right? So this is our open loop circuit. Down below, I'm going to include an idealized version of my feedback network, okay? So I want my feedback network to not load my amplifier. So I'm going to represent that by, on the input side, make sure I'm giving myself enough room here. So here's that port 2 of my feedback network. And since I don't want it to load my amplifier, I'm going to represent that on this side with an open circuit. On the opposite side, I'm going to represent my feedback network with a voltage controlled voltage source having a value of K times V out. And I'm going to put a box around this in blue. All right. And so this is my K circuit representation. Okay, so I'm going to go ahead and extend the output terminals of my output side of my open loop circuit so that I can connect my feedback network. So this is going to be the voltage V out. I want my output here, since I'm sensing a voltage, to be in parallel. Like so. And then on the input side, I need it to be connected in series. like this. And here is my source or signal voltage. Vs. Here's my feedback voltage, Vf. This is port 1 of my feedback network. And I measure my input resistance with feedback looking in through this set of terminals. And I measure my output resistance with feedback looking in through this set of terminals. All right. So we've drawn our system. Now let's start to analyze what's going on here, okay? This circuit exactly follows our general feedback structure signal diagram. And so we know that our closed loop gain AF should simply be A over 1 plus KA. All right. So that's where we're going to start. AF will be V out over Vs, and it should look like A over 1 plus Ka. Actually, before we do that, sorry, I'm going to move this down a bit. All right, no, I can leave that there. Sorry, I'm mixing myself up. Okay. Apologies. So what we are going to do right now is we're going to try to make this large structure look like an equivalent circuit that we can more easily kind of figure out what's going on, okay? And so what I mean by that specifically is we're going to represent this closed loop system by its own amplifier model, okay? So our equivalent circuit is going to look something like this. Let's just get out of the way. So our equivalent circuit, I'm going to do this in purple because it's going to be a blended version, should look something like this, where looking into the input terminals, we have our input resistance with feedback. If we look into the output terminals, we see AF times Vs, and then we're going to have ROF like so. I'm going to draw my purple box around this guy, try to illustrate that it's a blend of the two things that we have above it. And then over here is my source side, where I'm going to have my input signal Vs applied. Over here is my output side, where I'm going to measure my output voltage V out. So before we get back into what I was just talking about, all I'm trying to represent here is our goal here is to have a system where the output voltage is a scaled version of the input voltage. Exactly what we would expect an amplifier to do. Okay. Ideally, we can treat it like this simple system. And then we have an easy peasy gain characteristic in order to analyze. Okay, so we're going to figure out how to get there. All right, so circling back around to what I was saying a moment ago, and this is our equivalent circuit. We know that our gain with feedback, AF, should be of the form V out over Vs, which is simply our open loop gain A over 1 plus Ka. In order for us to determine our input resistance with feedback, RIF, we're going to look at the input loop. So looking at the input loop here, we can see that our voltage VI should simply be Vs minus Vn, right? So Vi is equal to Vs minus Vf. Well, Vf is just kV out. So this is going to look like Vs minus K V out, where V out can be expressed as our open loop gain A times our voltage VI, giving us finally Vs minus K A VI. So let's just scroll up here to make sure that we're all on the same page, right? So what I am suggesting here is that the voltage present at our output terminals is simply A times VI, because we have no load for there to be a drop over, and because our feedback network does not load the output at all because of this open circuit. There's effectively no current flowing through this loop, so that our output resistance doesn't really do anything, right? That's why we're seeing a very, very low output resistance, okay? And then we're just substituting in these relationships as we follow our signal path around. And so we found then that VI was equal to Vs minus Ka times Vi. And we can rearrange this to see that Vi times 1 plus Ka is equal to Vs, or in other terms, Vi is equal to Vs over 1 plus Ka. So effectively, our negative feedback here serves to make the input voltage across the terminals of the open loop amplifier as small as possible, right? In an ideal case, this would be 0. All right, now let's look at our input current, okay? So I, let's look at what we've got here. Is simply this voltage drop, Vi, divided by our input resistance, Ri. And so this is going to look like Vs over 1 plus Ka times Ri. Since our current II is the current that's being supplied by our voltage source, then that means that our resistance with feedback, RIF, is simply Vs over II, or 1 plus Ka times Ri. So we can see that series mixing boosts our input resistance, which is exactly what I stated earlier, but we can see mathematically why it's happening now, okay? To determine our output resistance with feedback for this system, I'm I'm going to scroll up here and we're going to talk our way through this, okay? So to determine our output resistance, we have to zero out our signal voltage. We've always had to do, okay? So we're treating this circuit now as if Vs is equal to 0. And we're effectively going to apply a test voltage source over here on the right-hand side. I'm going to, let's do this in pink. Let's call this 0. And I'm going to call this Vx. Let's call this Ix. And our output resistance with feedback is simply going to be the ratio of the voltage over the current. Just how we calculated output resistance for everything else, okay? So, excuse me. I'm sorry, what was that, Luke? So it won't be just R naught. And the reason why is because of this dependent source here, right? We do have to take its contribution into account, right? So if we applied Ohm's law, what we'll find is that we have Vx minus A times Vi divided by R naught. So let's just do that over here. So I'm saying for our output measurement, we have Ix is Vx minus A Vi over R naught, just using Ohm's law. Since Vi is negative Vf, right? And I'm saying Vi is equal to negative Vf because our source voltage is 0, right? So Vi should be Vs minus Vf. Well, if Vs is 0, that just looks like negative Vf. We're going to substitute in our relationship for Vf. So that's Vx minus A times negative K Vx, because Vx is our voltage applied across our output terminals here. Divide that by R naught. And with a little bit of math, we then have Vx multiplied by 1 plus Ka over R naught. And from this, our output resistance with feedback becomes R naught over 1 plus Ka. So again, we have mathematically explained why the parallel connection of the feedback network tends to cause the output resistance to decrease, which is a desirable property for voltage amplifiers. All right. So what we're going to talk about now is a practical case, right? This is how an ideal version would work. We don't have access to ideal amplifiers. We don't have access to ideal feedback networks, right? We make our feedback networks using passive components like resistors, capacitors, and inductors. Resistors, capacitors, and inductors have finite impedances or finite resistances that we have to deal with, which means they are going to tend to load the amplifier, right, when we connect them. So what that means is that they're going to have some influence on the open loop gain of the amplifier, of the amplifier. They're going to have some influence on the input resistance of the amplifier, and they're going to have some influence on the output resistance of the amplifier. In addition to the loading effects that we're going to see from our feedback network, we also need to take into account what happens when we have a finite load resistance and a finite source impedance as well. So our practical case system is going to look like this, all right? So I'm going to try to start over here on the left-hand side with our source voltage Vs. Like so. And I'm going to draw a set of terminals here, and I'll explain why in just a moment. And then this is our resistance R sig. So if we're looking in from the perspective of where we just have our voltage source applied, what we see is our input resistance with feedback. But if we're looking in through the terminals of our practical source representation, we are going to see the input resistance of the amplifier portion only. Okay. Now, I don't mean the input resistance of the open loop amplifier. This is more the input resistance of the closed loop system without this series contribution of RC. Okay. Now, draw a line over here, over here. So this is going to be our open loop amplifier. This is our input voltage, VI. This is our input current, II. I'm going to give myself a pair of terminals over here as well. And connected across these output terminals, I may have some load resistance RL that we need to account for. And then here's where I'm going to measure my output voltage. Looking in from here, we have our output resistance with feedback. Looking in from this set of output terminals, we're going to have this resistance R out, which is effectively simply our output resistance with feedback, neglecting our load resistance. Okay, so neglecting the effects of having a finite load resistance. Down below here, we have our feedback network. Where across the input terminals of our feedback network, we have our output voltage V out. We know that this feedback network should be connected in parallel to this set of terminals. And then over here to the left, we're looking at the output node of our feedback network. So just to be clear here, this is port 2, port 1. Here we have VF, and this network is supposed to be connected in series. Like so. All right. So this is our practical case with as many things that mess it up as we can possibly include, okay? So we're taking into account that we might have some signal resistance, so that our source has some sort of internal impedance that we may need to match to our system. We have a finite load resistance that we're trying to drive with this amplifier. Our feedback network is now a generic thing that may or may not load our open loop amplifier on both the input side of the amplifier and the output side of the amplifier. So the question that we need to answer now is, how do we make this circuit look like the ideal structure? Okay. The way that we do that is we introduce extra resistances that characterize the loading effects of the feedback network on the input side of the amplifier and the output side of the amplifier. And there are very specific rules that we do to implement this. Okay. So excuse me. Let's talk about this real quick right here, okay? So we are going to have a loading resistance R11. So R11 represents how the feedback network loads the input side of the open loop amplifier. Okay. It is determined by looking at our feedback network So here's port 1. Here's port 2. We look in with port 2 short circuit. This is how we mathematically determine what R11 is. And then because on the input side, our feedback network is connected in series, we connect R11 in series. And I'll draw that in a moment. Okay. R22 represents how the feedback network loads the output side of the open loop amplifier. And so what we do to determine that quantity, we take our feedback network, here's port 1, here's port 2, and we look into port 2 with port 1 open circuit. So to determine R11, we look into port 1 with port 2 short circuited. To determine R22, we look into port 2 with port 1 open circuited. Now, one last thing that we can do by analyzing our feedback network is to determine our feedback factor K, which will absolutely come into play as well. Okay. So our feedback factor K represents the transmission of our signal from port 2 to port 1 of the feedback network with port 1 open circuit. So effectively, what we have, something like this. Where we have our feedback network. Here is port 2. Here is port 1. We apply effectively a test voltage source here. Measure our voltage present at the output terminals of our feedback network, which is VF, under the constraint that this current is 0. And our feedback parameter K is then simply VF over V naught, with this current I being forced to be 0. So here's how we look at our feedback factor. All right, so we use this information from our feedback network to construct our A, or open loop circuit, okay? So our open loop circuit is going to look like this. Here we have our open loop amplifier. We should see that our signal resistance, our sig, is in series with our open loop amplifier. We should also see that our loading resistance, R11, is in series with our open loop amplifier. And here is our voltage VI. Here's our modified input resistance, including our loading effects. On the output side, we should see R22 in parallel with RL. And then here is our pair of output terminals where we measure V out. And looking in through this set of terminals is our output resistance of our open loop amplifier, including our loading effects. Our open loop gain, A, is simply our output voltage divided by our input voltage. And then from here, we have all of the information necessary to calculate the closed loop behavior of the circuit without ever actually analyzing the closed loop behavior of the circuit. So what I mean by that is, once we figured out what our feedback network is doing to our circuit, once we've calculated our open loop gain, taking into account all of the different ways that we are loading the circuit, we know that AF is simply A1 over one, excuse me, not A1, A times 1 plus KA. We know that RIF is simply RI times 1 plus KA. We know that ROF is RO over 1 plus KA. We know that RN is RIF minus R sig. And we know R out is 1 over ROF minus 1 over RL to the minus 1 power. So we're getting rid of that parallel load resistance to see just what the amplifier is. Okay. All right. So what I have done here is provided us the methodology with which we are going to analyze circuits. So now let's analyze circuits. Let's pull this back to something that makes some damn sense, okay? So let's say that we have the following circuit. I'm going to call this V signal because I don't want ambiguity. It is technically the source voltage here, but I want to make sure that I'm being as unambiguous as possible. So this is the input signal to our closed loop amplifier. Here is where we're going to take our output voltage. And instead of having a traditional, so this would be a common gate amplifier, right? Traditionally, we would bias the gate side with a resistor placed between VDB plus and the gate, and then another resistor between the gate and ground. We are going to include feedback by putting the resistor R1 here. And then here is our other biasing resistor, R2. All right, so before we really get started here, I want to introduce a couple of things, all right? Nothing remotely wild or crazy. I am simply going to acknowledge that the voltage drop over resistor R2 is my feedback resistor, and the gate source voltage is VI, my input signal to my open loop amplifier. Okay. So effectively just pointing out how this is set up so that we can figure out what our feedback network is and all that kind of good stuff. Okay. So to identify my feedback network, what I'm going to do is I'm going to try to see what component I have that links my output signal Vout to that quantity Vi, which in this case is just my resistor R1. Okay. So my feedback network, let's start with something pretty simple. We have our resistor R1. This terminal goes to amplifier output. This terminal goes to the amplifier input. So the expectation here is that port 2 should be connected to Vout and port 1 should be connected to Vout. Okay. So that's what R1 is doing. Well, so let's look at another thing here real quick. This bottom node of our feedback network is going to be ground because our output voltage is measured with respect to ground. So in order to connect this in parallel on the output side, we need the same set of terminals, right? Just going to identify real quick here. This is port 2. This is port 1. All right, so now let's talk about the remainder of our feedback network. We also have this resistor R2 connected between our input node and ground, which means we should have resistor R2 placed right here. Is it clear how I have defined my feedback network from an input-output port perspective based on how it's connected to the circuit, right? Resistor R1 links the output voltage to the input of the open loop amplifier. And then we also have this other contribution to the feedback network that is placed between R1 and ground. Right? Yes, Andrew. It's a voltage. How else? What would we measure the output voltage with respect to? Right. So this is the positive polarity terminal with respect to ground. This is the positive polarity terminal with respect to ground. We're treating all of these as if they were nodal voltages. Right. Does that clarify that? Okay. All right. So we have clearly identified our feedback network. Now we need to figure out R11, R22, and K. Luke. So that's likely going to come into play, but that's not part of the feedback network because that's not, the feedback network is added onto that amplifier, right? So that would be part of the open loop amplifier, but not part of the feedback network. Right, so we're seeing how this the inclusion of these two extra resistances, what impacts they have on the open loop amplifier's performance. Sorry, couldn't think of a word there. Okay. How do we measure R11? We look into port 1 with port 2 short circuit. So that would place resistor R2 in parallel with resistor R1, right? So R11 is simply R1 in parallel with R2. How do we find R22? We look into port 2 with port 1 open circuit. So that means we're going to see R1 in series with R2. How do we find our feedback factor? Okay. So this is a simple voltage divider circuit. And we want this voltage measured across resistor R1 divided by this voltage, which is the voltage drop over those two in series. So it should just be R2 over R1 plus R2. We could formally do it with a test source and all that kind of stuff if we need, right? All right, so we figured out what our feedback network is doing. Now we're going to redraw our circuit. So here is VDD. Here is RD. Here's V out. Here's I'm calling this VN here specifically, even though this is where we would apply our signal voltage, because we are looking at this as an open loop amplifier configuration, trying to figure out what the open loop gain is. So VN, VSIG, they all effectively represent the exact same thing here. But I'm using VN in particular because I want to show that this is the input signal to our system. All right. So R11 going to appear between where we had our connection to our input signal VGS and ground. R22 is going to appear between where we had our connection to our output signal. Now we want to determine the open loop gain this amplifier configuration. What kind of amplifier is this? Pardon? Common gain. Okay. So what should our open loop gain be based on this configuration? And let's neglect channel length modulation for the sake of argument. So it would normally be simply GMRD. But now we have R22 in parallel. So our open loop gain A is simply GM RD in parallel with R22. And from this, we know that our gain with feedback should be GM RD in parallel with R22 divided by 1 plus K R2 over R1 plus R2 times A GM RD in parallel with R22. Our input resistance with feedback, RIF, will be our normal input resistance. Luke, as you correctly observed earlier, our normal input resistance here should be 1 over GM. That's going to be boosted. So we're going to have 1 over GM times 1 plus K A and we're going to have an output resistance with feedback. So what would our output resistance here without feedback normally be? Exactly right. RD in parallel with R22. So this is going to look like RD in parallel with R22. And here we have 1 plus R2 over R1 plus R2 times GM times RD in parallel with R22. And close this bracket. We now know how our closed loop amplifier behaves based on our knowledge of how the open loop amplifier works. The only particularly new thing that we had to do here was to identify what contribution our feedback network added to the system. Okay. All right, so we are done for today. We're going to work another one of these voltage amplifier circuits on Friday. I'm going to bump the difficulty up by using 2 amplifiers and chaining them together with a feedback network, and we'll talk our way through that. But it's effectively just this again, and then we'll move on to our other amplifier configurations. I have the first 4 problems of your homework set finished. I'm going to draw out using my computer program the last 3 circuits that I want to give you guys to do and get that to you tonight before I go to sleep. I hope I can do it tonight before I leave at 5, but we shall see depending on how many of you guys come knock on my door in the morning. My goal is to get your exam up for Friday. Probably later on in the day on Friday, but I hope to get your exam up for Friday so that you have a full week to work on stuff. I'm going to give you guys the exact same opportunity that I gave to my Circuits 2 students. And so what I mean by that specifically is things are going to be officially due Friday, May 20th at 5 p.m. because that is when the quarter is over. And so I can't make anything due after that point. Unofficially, if you get it to me by Sunday at midnight, we're good. No late penalty on either the exam or the homework set to give you guys some more time to work on things and balance other credits. Okay. I do have to have time to grade things and all that kind of stuff. So yeah. So does that seem wildly unreasonable or anything? You have effectively 2 assignments left. You've got about 11 days to do them. I'm going to try to give them both of them to you as soon as I possibly can. Andrew. We still have class. No, that seems kind of pointless. Like, I'll be here to answer questions if you guys have anything, but as far as having a lecture doesn't make sense because it was supposed to be a test day and all that kind of good stuff. So yeah. I'll be here if you have questions on that Friday, but you don't have to show up unless you feel the need to come talk to me about something. Does that sound okay? All right, use that time to work on your test, you procrastinators. All right, I can't bitch too much because I'm a huge one as well. Or otherwise your exam 1 would have been graded 2 months ago. So, all All right, thank you guys, and I'll see you all on Friday.